Thank you. Thank you for the introduction. Thank you for being here. It's very exciting to have the opportunity to share with you some of the work that my group and I do on low-mass stars. Just for context here, we're talking about main sequence stars, less massive than the sun, so G, K, and M dwarfs. And yes, thank you for the application update. And what I'm going to tell you about is what we've learned over the last few years, thanks to just the wealth of data that have come through primarily from space-based missions. Before I do that, though, I want to provide some context for why people, even people who perhaps don't care that much about the properties of low-mass stars, might find this work interesting. And I'm going to start here with this artist illustration of the Kepler mission. So that's the Kepler telescope here. Here's a pretty illustration of the stars that Kepler observed. And you'll recall that Kepler's goal was to observe the same part of the sky for essentially 4 years continuously in order to answer a basic question, which is, are there planets around other stars? And what we learned from Kepler, if I had to summarize it briefly, is that in fact there are planets everywhere. Okay? And this graph, I think, illustrates this really nicely. So on the x-axis here, you have the year of discovery, and the y-axis is just a cumulative number of planets that have been discovered over time, right? And so when I was an undergraduate student in the 1990s, it was still possible to have real arguments about whether or not there were planets outside of the solar system. And by the early 2000s, you can see that the radial velocity technique had started to find primarily hot Jupiters, as we know now. And then the launch in 2010 of Kepler, shown here, and then a few years later of TESS, really has made the number of exoplanets discovered explode. And you can see that we're now over 6,000 of these planets. And in fact, if you extrapolate from this plot, we now say routinely that there is, on average, a planet for every star in the Milky Way. So in 30 years, we've gone from a situation where we could still argue about whether there were any exoplanets to one where we say, actually, we think there's one for every star in the Milky Way, which is truly remarkable. Okay. So I think this is a settled question, right? We now know there are lots of exoplanets out there, and we can turn to questions that are probably more interesting, such as how many of these are actually habitable? Now, the habitability of a planet is a complicated concept, and I'm not going to go through all of it, but I'm just going to start by reminding you that the basic idea is that in order to be habitable, a planet, an Earth-like planet, needs to be at the right position relative to its star for it to maintain liquid water on its surface. We know liquid oceans are critical to how life developed here on Earth. And if the planet is too close in, the water just evaporates off. You lose all your oceans. You become very dry. If the planet is too far out, then the water freezes. And maybe you can have oceans underneath, blah, blah, blah. It gets complicated. But essentially, you're not in an Earth-like situation at that point. So it makes sense to look for planets, Earth-like planets, that are in the right position to maintain liquid water on their surface, right, as a primary criterion. And the good news there is that we seem to be finding these planets. So this is a plot from the Carmenes survey. This is a survey that uses a dedicated telescope in Spain. I'm showing it because I've actually been there, so I got to observe at that observatory. And what you're looking at here is on the x-axis is the orbital period of the planet versus the mass of the star, shown here by its size, right? So the sun is around here somewhere, and then we're going down to lower mass stars here. Now, as you go to smaller masses, the habitable zone comes in relative to the star, and so that's what you're seeing here, is this strip here corresponds to, on one end, maybe Venus, on the other, maybe Mars, right? And where you're looking is for planets that fall in there. And these little symbols here, those are Earth-like. And you can see that particularly around low-mass stars, we're actually doing a fairly good job at finding planets in the right place of their, in their systems for life potentially to arise in some kind of water environment. Okay, and here's just an example from that was at the time when I put together this slide. Recent. This is now a couple of years ago, I think, but of an orbit of an Earth-like planet around one of these low-mass stars, and it's in the habitable zone. Okay, so the point is, these Earth-like planets in the habitable zone exist, and we are finding them. okay? But that's a necessary condition, not a sufficient condition, right? There are other conditions that a planet has to meet in order to be considered habitable, right? And here again, I'm not going to go through all of the possible ways that you could define habitability. That's complicated, but one that I want to impress on you, because I think it's not fully appreciated, is the question of how old the planet is. Okay? And so to illustrate that, this is an artist's impression of the very early Earth. This is the geological period known as the Hadean. So it comes from Hades. It means like the Earth was hell. This is the first few 100 million years of the Earth's history, and you can see the crust is still forming. There's lots of volcanism. It's also perhaps the period of heavy bombardment where lots of things are flying around in the inner solar system. So it's really not a very habitable environment. I don't know why the sun is giant in this image. That's the one thing here that the artists, it's an artist impression, okay? From the Daily Mail, no less. So make of that what you will. Okay, and now, of course, we have a very habitable planet, right? And what's happened between those two is we had 4.5 billion years, give or take, of evolution to occur that have changed the conditions on the Earth such that life is able to emerge and thrive. So when you're looking at these exoplanets that you're finding in the habitable zones of stars, one question you might just ask is, well, how old is that planet? Right? Is it more like in the Earth age, or is it actually in a much earlier stage of evolution where maybe it's not so ideal conditions there for life to emerge? Now, of course, it turns out that that's a really difficult question to answer directly. Like, we barely observe planets directly. There's some direct imaging and so on and so forth. But the bottom line is we're not going to get the ages from the planets themselves. So our best hope is really to try and determine the ages of the stars, right? The stars and the planets form at the same time, more or less. And the stars, at least, we can observe. Okay, so maybe the stars can tell us how old they are, and that way we'll know how old the planets are. Well, the problem there is that there's only one star for which we have a precise and accurate age, and that's the sun. And the bigger problem is that that age does not, in fact, come from our observations of the sun itself. It comes from rocks, okay? And specifically meteorites, and specifically inclusions in the meteorites, these little things down here, called carbonaceous chondrites, which are unprocessed material from very early on in the history of the solar system. And it's by dating those carbonaceous chondrites that we get what is in effect a lower limit on the age of the sun. Okay. This is not a technique that we can apply to stars across the Milky Way. Right? We need something observable as opposed to actual samples, right, to come from those systems in order to try and get at the ages of the stars and of the planets. So the question is, are there actual observational properties that change over time of stars on the main sequence that we might be able to use, since we don't have access to things like this, in order to derive ages? And it turns out that, yes, thankfully there are some. Okay? And so what I'm showing you here is a very famous plot from a very short paper in 1972. This is kind of like a mandatory plot if you're going to talk about anything related to main sequence stars and their ages. It's a 2-page paper in which Andy Skumanich summarized essentially the state of observations of main sequence stars over time from the 1960s through the 1970s. So age here is on the x-axis, so this is 100 million years, this is 1 billion years. And there are 3 lines here, and we're going to focus for now on the middle one, which measures how fast the stars are rotating. So fast rotating stars are up towards the top, slow rotating stars are up here at the bottom. And what you can see is that there seems to be this smooth decay in how fast stars rotate over time. Okay? And in fact, Skumanich parametrized this by saying that the rotation rate goes as 1 over the square root of the age. So this is perfect. If this relationship holds, then you measure the rotation speed of a random star and you just read off this relation how old it is. That would be great. Okay. However, there are a number of things that should give you pause here. The first, of course, is that this is based on 3 data points. So this is one of those wonderful things in astronomy where we have a law based on 3 data points. And those 3 data points are the Pleiades, the 7 sisters, the Hyades, another well-known nearby open cluster, because those are clusters we can get ages for those from isochrone dating, and then the sun. And the gap here, of course, this is a logarithmic, this is a log-log plot, so the gap here is only a few hundred million years, but here you have 4 billion years, roughly. So you're hiding a lot of time, right, in this relationship. And in fact, Skumanic himself in this plot shows you that fundamentally, if you don't know the age of the Hyades that well, then you might wind up shifting this data point over, and the shape of this relationship would change pretty significantly. And as it turns out, most people would say that this age for the Hyades is not great. It's probably a little bit older than this, and so it does shift this over. But that's kind of made up for the fact that the Pleiades is probably more like over here too. So the shape of this relationship doesn't change that much relative to this prediction, but you know, it's still 3 data points and covering 5 billion years worth of time. The other thing to point out is that this is based just on sun-like stars. And when I say sun-like, I mean really G stars. And most of the stars that we're actually interested in right now as we're thinking about habitability are later type, lower mass stars than that. And that's for a whole host of reasons. For one, there are just more of them, so it's easier to find, you know, it's easier to look for the planets around them because there are more of them. Also, it's easier to find planets, Earth-like planets in Earth-like orbits around smaller stars. So the bottom line is we'd like to know whether or not modern data supports this, and we'd also like to know whether or not it extends to lower mass stars than the handful of G dwarfs that were being studied at the time. So I'll say very quickly, to kind of save you the suspense, it does still seem to work for the G stars, so that's the good news. On the other hand, it does not seem to work at all for the K and M stars, so that's the bad news. Okay. So let me get into that a little bit. I'm going to show you now what we can do with more recent, more modern surveys that really have transformed our ability to measure rotation periods in the last 10 years. And so the first thing I'm going to highlight here is a paper that was led by Reina Rampali, shown here, who just finished her PhD at Dartmouth. And this was based on K2 observations of a cluster known as Persepi. Persepi is about the same age as the Hyades. So when you saw the Hyades in that previous plot, Hyades and Persepi are essentially, you can think of them as the same cluster. They're not the same cluster, but they have very similar properties. And K2 was the follow-up, the continuation of Kepler after a couple of its wheels broke. And the big thing was that the K2 field was able to observe thousands of stars in Persepi at once, and so gave us just this incredibly rich data set for the cluster. And so I think it's important to give some sense of how transformative that is. So this is like the most up-to-date paper on rotation in stars in Persepi before K2. And this is from 2011, and so you're seeing mass here increasing to the right. So the lowest mass stars are here, the sun is here. And this paper added, 15 rotation periods for these M dwarfs. These are M dwarfs down here that you're seeing here highlighted. Up here is just a line that represents the existing data for high mass stars, of which there were maybe 15 periods measured at the time. And I sort of challenge you looking at this plot to figure out some kind of pattern. Like, what's the connection here between the high mass behavior, the low mass behavior? You tell me, right? So what happens when you get 1,000 of these? Well, you populate this plane obviously much better, right? So there are something like 1,000 periods here. Mass now is plotted differently, so it's going towards the left because we're actually using the Gaia colors here. That's the native thing that we measure the stellar properties with. So the blue massive stars are over here. The low mass stars that were in that plot are down here, and here's the rotation period. And if you clean that up so that you focus only on single stars or stars that you think are single. Now you can see some real structure here. So here are the high mass stars that were represented by that line. And then you can see here are the low mass stars, and they actually are connected. Those populations are connected. There's this kind of waterfall that I like to call it the waterfall. We never gave it an official name or anything. But you can see that for high mass stars, so maybe up to about an M1 or M2, high mass in the context here of low mass stars. I realize this is all relative. So let's say up to the mass of the sun and a little bit beyond, down to maybe 0.6 solar masses, you actually do have a single valued relationship between the rotation period and the mass at this age. So that's nice because that's what you want to track. And then when you get down into the M dwarfs, the situation gets much messier. You have a much wider spread in rotation periods. Okay. So this is what a single cluster allows you to do now. You can really, with the large set of data that you have available to you, you can really characterize the rotation periods across lots and lots of stars at that single age and say, now let me look at the evolution. Let me look at clusters of different ages to see how these properties are changing over time. Right? And so I'm going to walk you through what that looks like. So switching the axes here to effective temperature. This is because some of these data are pre-Gaia, so we just find we use temperatures as the plotting unit here. But it's the same idea here. The more massive stars are here to the left, the less massive ones are over here to the right. And this is from Luisa Rebel's 2016 paper. And you can sort of see that that single valued relationship between temperature or color or spectral type or mass and rotation exists out to some spectral type, some mass here, and then again it gets to be a little messy. It's a little hard to see what's happening here. This is a young cluster. In fact, some of these stars here are still contracting onto the main sequence. They haven't fully gotten there, so it's a little complicated. But now if you add Reyna's results for Persepi, you can start to see actually a pattern emerging. And the pattern is kind of what you expect from theory, which is that all of these stars should be losing angular momentum as they age, right? So this goes back to the Skumanich plot. Why are the stars rotating more slowly when they're older? Well, they have magnetic fields. Those magnetic fields carry away charged particles. Those particles, that represents a momentum loss. It acts as a brake. It slows down the rotation of the stars. And so over time, if I have a population that starts out rotating relatively fast, I expect all of those stars to kind of shift up in a sort of smooth way as they get older, right? And you can see that. So if you look at, the 6,000 Kelvin, like the sun-like stars here, they've clearly slowed from a few days to about 10 days over that time period. And you can see also that it seems like these stars down here that were rotating pretty quickly at the age of the Pleiades have now actually also joined this sequence. Okay? And so what you'd like to do is to play this movie forward in time. Okay? And say, all right, well, what happens if I predict into the future based on this? What would I expect? Okay? And so for now, I'm going to focus on the G stars, right? Because that's where we started with Skumanich. That's our star. So let's ask, okay, if I assume that I know the behavior of these stars, right? I can parameterize this with some kind of polynomial, and I apply a Skumanich-like law. So I say, I expect these stars to slow down by so much over so much time. Where would they fall? Well, they would fall on this yellow line. And where is the sun? Well, the sun is right there. So for the G stars, it looks like it works. It looks like I can take one of these younger populations and apply a standardized spin down model, so how it's losing angular momentum, and come up with the rotation period of the sun. Okay, that's great. That means that if I go back to the question of finding ages from rotation periods, for G stars, this seems like it would work pretty well. What's not clear at all is what's happening with the lower mass stars. Okay? And so, again, these are the ones that we probably are more concerned about at this stage because just the nature of our surveys and where we're finding exoplanets. Also because this is my biased opinion, they're a little more interesting than G stars, but that's a whole other story. Well, when we started looking at what happens at older ages, we immediately ran into something that was kind of confusing. And so this is from a paper I led back in 2018, where we looked at one of the clusters that was in the original Kepler field, 1 billion years old. And they'd noticed already when they measured the rotation periods for stars in that cluster back in 2011, that there seemed to be this kind of flattening of happening of the rotation period sequence. So you can kind of see here the rotation periods sort of flare up, and these flatten. And so back in 2018, I said, look, this is kind of curious. Like for the stars like the sun, I'm seeing some spin down over 300 million years. Like the stars are slowing down, they seem to be moving up. But as I get to lower mass stars like the K stars, I don't see that. It looks like they're overlapping. And so we went back and looked at this more carefully a year later. This is work led by Jason Curtis, who's a research scientist in my group, where we were able to retrieve more Kepler periods for lower mass stars in the cluster. And now I hope I don't have to convince you that what I was seeing was real. That is, if you look now at the K dwarfs and up until the early M dwarfs, the rotation periods are actually indistinguishable at 1 billion years and at 700 million years. Okay? And this orange line is just a prediction. So in the same way that I predicted where should the stars be at 4.5 billion years to ask whether the sun was in the right place, here I'm saying, okay, I'll take Persepi, I'll evolve it to 1 billion years. Where should the stars be? They should be along this line. They are not. So these stars are lying to us about their age, right? Kid, you know. So all kind of movie celebrity kind of analogies you can use here. They're acting younger than they are. They're trying to look younger than they are. The bottom line is that you can't use their rotation period to tell you how old they are. Okay. And we've confirmed this now looking at several other older clusters. Okay, so this blue line is again one of these predictions based on Persepi of where the stars should lie at about 2.5 billion years. And the blue dots are actual measurements. Okay, and you can see now for the late K dwarfs and the M dwarfs, they're rotating about twice at half the period, twice as fast as you would expect at that age. Okay. Again, if you go and look at the G stars, they are where you expect them to be, so that's great. But if you go and you read many of the exoplanet papers, right, they use the rotation periods of the host stars, often late K or even late M stars, to tell you how old the systems are. And the bottom line is that I would be very, very skeptical about that, because we don't really understand how long this spin down, this change in the spin down lasts. We know that when you go and look at M stars in the field, they are rotating at periods of 80, 100 days. So eventually they must start to slow down again. But for now, we don't really understand why this happens or how long for, and that makes figuring out the age of the star based on its rotation period highly uncertain, to say the least. Okay. I just want to highlight there's another cluster in here at 1.6 billion years that shows you what I mean. At 1.6 billion years, the K stars are still overlapping largely with Persepi. At 2.5, they've started spinning down again. But the later M stars don't seem to have done that quite to the same extent yet. So there's clearly some kind of different time scale here that depends on the mass of the star. All right, so your natural question might be, why is this happening? And my answer is, I don't know. There are a couple of theories that people have tried to invoke. One is that these stars have fast rotating cores, and maybe those cores can inject new angular momentum into the star's envelopes, and that offsets the loss from winds. That to me seems a little troubling because it requires some very fine tuning in order for that to happen. Another model is just that you have changes in the overall structures of the magnetic fields. We know that happens with the sun. That impacts the winds, how fast they are, their structure, and maybe that's reflected then in the angular momentum loss somehow. But the bottom line is, I don't know. Okay, I'm going to change topics now. So that was the first thing I wanted to present was just, what have we learned about rotation from this work. Now I want to give you a sense of how really Gaia has changed our perspective and our work so tremendously over the last few years. Gaia undergirds a lot of the work that I just described. I just didn't make that explicit, and now I think I want to make that a little bit more explicit. So this is Tristan Cantat-Godin. This is from 2018. This is just a visualization of the membership of a number of clusters, open clusters, in the nearby galactic plane. Okay? So we're going out to about 300 parsecs here, and I think I have two representations here, sort of from the top and here on the side, so you can see some of these sit a little bit below the plane. And you can see they look like fairly well-defined balls of stars distributed more or less randomly around us. Fine. Stephen Meingast, shown here as a postdoc at the University of Vienna, said, we can use Gaia to do more than just redefine the membership in a classic way. Let's look for things that are co-moving. So let's take the clusters that we know, plug them into Gaia, and try and find things that are moving together with the stars that we think are already part of those. And what he found is all of these, what he would describe as halos and tails to those same structures, right? So I'll just flip back and forth. These are the same clusters, but now rather than using sort of historical definitions for the membership, we're expanding that membership to think of stars that are together moving through the galaxy. Okay, and you see the picture is starting to get very different. Maybe some of these things aren't even distinct anymore. And then Marina Kunkel, shown here, around the same time, did an even bigger, less confined search for things that were co-moving. And now if you look at the space around us, we're just like, we're living in a swarm of these co-moving structures. Okay? All right, so I'm just trying to impress. This is kind of the classic picture of where these clusters are. This is our current potential picture. Okay? And, yeah.
I'm just curious, the structure for this plot and the previous plot, for example, the purple, they're actually different. I'm just curious about them.
Yeah, so the differences come down really to the details of the techniques that were used to try and define these co-moving. Honestly, I can't remember exactly why this one looks different. I think, I could get into this more, but what I would say is that each of these uses slightly different modifications to clustering algorithms. Typically it's HDB scan, but there are other versions that people use, and they have different requirements on the quality of the data, how co-moving is co-moving, whether or not you limit the volume, and so on. And so that leads to these somewhat different looking structures. But your point, I think your question raises an important point, which is that you can't just take this at face value, right? These are products of choices that are made in how you use the data to identify these structures. And that's exactly what motivated us to say, okay, this is incredible, but now we need to go and look at these carefully to see really, are these all clusters real? Are all these stars really associated with each other? What can we determine that before we do anything else? Yeah. And so I just want to put up this picture that shows what the so-called Theia catalog. So these are the Kunkel and Covey structures. This is centered on the sun, and I think this goes out about a kiloparsec. And you can see each of these dots is one of these structures. Many of these look like classic clusters, but many of these things do not. They look much more filamentary. They wrap around huge areas of the volumes of the sky. There's just a diversity and a wealth of structures out there now for us to play with, as opposed to the 5 or 10 classic open clusters that we knew of before. And so that opens up a very exciting possibility that we can now study the evolution of things like rotation just with a much larger set of clusters that give us benchmarks at different ages to answer the question of how the stars are changing. So that led to us to design a survey. Every survey needs an acronym, of course, and so I'm very proud. I came up with this one day when I was washing dishes. So this is a marmot. I'm not sure how common they are in Taiwan, but this one is obviously observing a cluster. And the acronym stands for membership, because membership underlies all of this, to come back to the earlier point. Abundances, because some of our work is interested in the chemistry of these stars. Rotation, hopefully I've motivated why we care about the rotation. Magnetism, which is another dimension that I'll get to in a second. And of course, over time, and that gives you marmot. Thank you very much. Thank you. Okay. Thank you, thank you. So I just want to try and summarize now some results here from the marmot. And I'm going to start with another cluster, Comaburenices. This is a cluster that we've known about for a while, but has always been very hard to study. And that's because it's nearby and it's very dispersed. So here on the right is just an RA deck plot. And so you can see it's spread over like 10 degrees here in both RA and deck. So, you know, large areas of the sky. And in proper motion space, which is how people often found these things, they sort of sat out relative to the galactic background. Like you essentially expect the galactic background not to be moving, and so you look for things that are clustered away from 0, 0 in proper motion space. I mean, yeah, it's there, but if I took away that red circle, I'm not sure you would believe me, right? And this was the state of the art. This was Adam Krause's PhD thesis work with Lynn Hellenbrand at Caltech. This was really the state of the art back in 2007, okay? So I won't go through all the ways in which Gaia has improved this, but now last year we published this paper where we went back and redid the membership analysis for this. We found that in Adam's original catalog there were all kinds of background giants that were contaminants because we didn't have parallaxes. So we didn't know how far away they were. Gaia immediately identifies those as background giants, and so we can remove them. And you get this really nice color magnitude diagram, the Gaia color here, the magnitude here. Here's my main sequence. And I can use the top of that main sequence to fit some isochrones to get an age for this cluster. And the age that I get out of this is about 700 million years old. And so you might say, well, you just told me you have in Persepi and Hyades, you have 2 clusters that are already that age. So why do you care about a third one, okay? And the answer is that it turns out that Comabur has an interesting metallicity. And that's what this plot is intended to illustrate. So here we've narrowed the temperature range that we're looking at from sort of mid-Fs to early Ks. And we're getting metallicity measurements from Lamoste. And at the top here is Persepi, and at the bottom here is Comabur. And you can see, like, the absolute numbers here don't matter so much. There are all kinds of issues with that. But the offset here is the thing that you're interested in. And the bottom line is that Persepi is actually slightly metal rich, 0.2 dex. And Comabur is actually consistent with the sun. So 0. So there's this 0.2 dex difference in metallicity, which for a lot of you who do metallicity work, that probably doesn't sound like a lot, but for open clusters is a lot, because most open clusters actually are right about here. There's very little variation in the metallicity. And so this gives us an opportunity to ask, how much does metallicity matter when we look at how rotation periods are changing? All right, so we make a killing on periods. So here's just another plot showing how pathetic things were in the early 2000s. You could, publish 10 rotation periods, and that would be a very exciting result. Here's how it looks now. This is primarily from tests, along with some ground-based measurements. Now we have really filled out the high mass sequence here that was just being hinted at, and then we also get into the late type lower mass M stars here again. So that's exciting. But what's more exciting is you can do a comparison between the period distributions from Persepi and the period distributions of Comabur and ask, does metallicity make a difference? Okay? And so what I'm showing you here is that those 2 sequences. Now this is all Gaia colors, so again, more massive stars to the left, lower mass stars to the right. Rotation period in days. The empty squares here in the background are Persepi, and the orange stars are Comabur. And to help guide the eye a little bit, I've drawn this line here, and what you can see is that to the left of that line, so of the more massive stars, essentially you don't see a real difference in the rotation period distribution. Like they follow each other very closely. On the other hand, on the right-hand side, there looks like there's an offset. And if you go and you do the statistics, you do see, in fact, that there is an offset between these two distributions. Like Persepi stars, there are two ways of looking at this. At a given rotation period, they tend to be redder, or at a given mass, they tend to be rotating more slowly. Okay. Now that's interesting, but it's also somewhat misleading because metallicity changes the color of a star. So that if you're looking at two stars that have the same mass but different metallicities, the one that's more metal rich is going to appear redder. Okay? And so you can plot this now in mass space instead. So now confusingly, like mass, right, is going this way. So here's the high mass end, here's the low mass end. The spectral types here are along the same. And now if I draw that same line, so roughly between the M0s and the M3s, what you see is to the right, now they align. Right? So it looks like, in fact, there is no difference in the rotation period distribution for those low mass stars, despite there being a difference in the metallicities. On the other hand, now where you see is that there's a difference up here with the more massive stars. It's particularly visible for the K dwarfs. Okay. So what's going on here? Well, metallicity changes the convective properties of a star. And specifically, the convection zone gets deeper into a star when you make it more metal rich. And so that is in turn going to impact the dynamo, and it's going to impact the torques, the winds that the stars produce. And so you expect more metal rich stars to slow down faster. Okay? And so that's kind of what you're seeing here for these stars. You're not seeing it here, and that may be because many of these stars are actually fully convective. But we don't really know. Why? Because this is the first time that we've been able to see that metallicity does have some effect. So what's the bottom line here? If I'm trying to use the rotation period to derive an age, for a G star, I don't care about the metallicity. Like if I'm working in color space, it's totally fine. For the M stars, it's a problem because differences in the metallicity are going to impact what I expect to see in terms of where the rotational distribution. Okay, let's see. How much time do I actually have? Sorry, when did I start? I lost track of. I want to make sure I leave some time for questions. So.
Yeah, well, 20 minutes.
20 more minutes? Okay, so 10.
50.
Okay. Okay, all right, so then maybe I do. All right, so I want to talk a little bit about what kinds of clues we have that the magnetic properties of the stars may actually matter in this discussion as well. So this is just a portrait gallery of some of the stars in Coma-Burr for which we obtained optical spectra with the goal of measuring the H-alpha line. And so you can see as you go from massive stars to less massive stars, you go from having H-alpha in absorption to seeing very strong emission. And so H-alpha is a frequently used line to diagnose chromospheric activity in stars. These stars are not hot enough to have, the fact that you're seeing the line in emission is telling you that there's additional heating of the atmosphere that's happening, and we think that's due to the magnetic fields. Okay, so measuring the H-alpha line is a way to tell you how magnetically active the stars are. And one of the key things that we found when we looked at the H-alpha properties of these stars is that the stars in Coma-Burr that are rapidly rotating M dwarfs are essentially all saturated. And what does this mean? This means that their level of magnetic activity has decoupled from their rotation rates. Normally you would expect that as a star, you spin a star up, make it rotate faster, it should become more magnetically active, and vice versa. If you spin it down, it becomes less magnetically active. But it turns out that there's a limit to how much you can spin it up and increase the magnetic activity. Past a certain point, all the stars essentially will plateau in their magnetic activity, and it doesn't matter how much faster you make them rotate. And so one of the the key pieces of information that looking at the magnetic activity provided for us was to say all the stars below this line here are saturated. That is, if I spin them up faster, they won't produce more magnetic activity, whereas all the other ones here, for which I have H alpha measurements, most of them, there are a few exceptions here, but almost all of them are unsaturated. So they follow a more traditional relationship. And so the bottom line is that this is telling us that magnetism is a key component of this picture. We can't ignore what's happening in terms of the magnetism of these stars when we try to understand their properties over time. And the big thing is that for these stars that are saturated, the winds no longer depend on the rotation period. Okay? So they've become independent of how fast the star is spinning. All right. The point I want to make is that we can't ignore activity, right? And that's the line here at the bottom of the Schumann plot is actually a magnetic activity line. Here he was using calcium H and K, which is a different indicator of magnetic activity from H alpha, but it's another chromospheric one, and making a very similar argument that that was decaying in a similar fashion to the rotation period. Up here, if you're interested, is lithium, which is a whole other story, but this is a magnetic activity tracer. And the bottom line is that, as that previous discussion I hope convinced you, magnetism is much more complicated to understand, okay? Because there are these different regimes. The dependence on rotation is not super clear, but there seem to be different regimes where if you rotate really fast, you saturate. We don't really understand that phenomenon. And furthermore, the availability of data is just not as great right now to do these kinds of systematic surveys where we look at how activity is changing in the same way. So I just wanted to show you one example of this. This is from Alejandro Núñez, who's another research scientist in my group. And this is looking at X-rays. So now we're looking at the corona, where, again, magnetic heating is responsible for producing million Kelvin temperatures, so you get X-rays. And this is just asking over time, right, so a billion years here, how is the X-ray emission from these stars changing? And it does look pretty smooth for G dwarfs, and it does look not completely incompatible with the kind of relationship that Schumann had predicted. Okay, so again, the G dwarfs seem pretty well behaved. The problem, well, I should first say that if you look at K dwarfs and M dwarfs in this way, this is from a paper we published back in 2016, you see this similar kind of decay. You'll note that the timescales are not the same though. Okay, so they don't behave in exactly the same way. And the other problem is that there's not a huge amount of information at older ages. And so if you focus in on the G-dwarf relationship, for example, here's the sun between solar minimum and solar maximum, and it does not fall on the relationship that you see from the younger G-dwarfs. So it's entirely possible that there's some break in this relationship that we're not seeing just because we don't have the data. And so one of our goals has been to try and fill in this picture by getting older stars, possibly in a cluster like NGC 752, which I mentioned earlier, which is 1.5 billion years. If we could measure some X-ray emitting stars in that cluster, that would allow us to put another data point here, and we could try and fill in what is now a picture that is mostly from field stars with very uncertain ages and the sun. And we assume this smooth decay, and I, for one, don't really believe that that's what's happening. Okay. So we need more benchmarks. All right, so the last thing I'm going to mention here is the ultraviolet. So the ultraviolet tells you about another layer of the stellar atmosphere that's heated by the magnetic field. That's the transition region between the chromosphere and the corona. And I'm putting this up. This is slightly hypnotizing, so don't watch it for too long. This is a small privately run satellite telescope that launched back in November called MOVE that is doing sort of low resolution, broad spectroscopy of nearby stars that includes the ultraviolet. And so this for us is very exciting because it's an opportunity to try and ask, what do these stars look like? I mean, the focus here is on flaring, so on magnetically very active stars. But we actually know very little about the baseline emission in the ultraviolet from these stars at all. And so in order to kind of construct like what we expect magnetic activity to look like in the ultraviolet, we need just some baseline measurements, and that's what we're hoping to get with MOVE. And MOVE is a 3-year project. So we are entering into year 1 now. We haven't fully started the survey, but I think it's supposed to start in the next couple of months. And there are at least 3 science themes here that are relevant here. So characterizing young planet hosts with MOVEs. Okay, so this is, we want to understand the ultraviolet environments that are shaping these planets. Characterizing habitable worlds observatory targets. So this is supposed to be our next great flagship mission to understand exoplanets. Can we say something already now about the potential habitability of these planets based on the ultraviolet emission coming from their host star, which has a lot to say about potential habitability. And then what I just told you about, which is the quiescent UV emission in low mass stars, which is sort of baselining what those properties look like. And I mention this because MOVE is actively looking for partners. So if these science themes or other science themes are of interest to you, I'm happy to talk to you more about how MOVE is structured. Okay, so in conclusion, and I always have a hard time figuring out how to conclude these talks, so I did the thing that, of course, all of us do these days, which is I asked ChatGPT, what are some good reasons to study low mass stars in open clusters? And it gave me this following list of good reasons that I actually thought were pretty good. And so with that, I will end my talk and take any questions. Thank you.
Any questions from audience?
Oh, okay. See, I was confused because that clock has a different time than my watch clock, and I was like, what am I doing here? I'm going way over where I thought I was. Yes, sorry, questions?
Yeah, thank you for your talk. So I'm curious about the rotation period and the colors plot for different ages.
Yeah.
So based on your later part, can I try to understand it? So the lower mass part is connected to the waterfall region, depend on the metallicity.
So in the plot that I was showing you, like one like this, there is actually not, I mean, off the top of my head, I don't know the metallicities of all of these clusters, but my guess is that they're all basically the same. They're all somewhere between 0.15 and 0.2 dex. So here you're not seeing any kind of metallicity effects illustrated.
So the behavior here is not linked to the behavior of the metallicity.
No. So what you're seeing here is, right, so if you imagine that you take a population that has, a random distribution of rotation periods, right, that reflects like star formation, right? So they come out of the star formation period, and they're basically distributed between 0 and 10 days evenly across these masses. And what happens is pretty quickly you start to see structure, and that's because the faster rotators have the strongest winds. And so they sort of all converge onto one of these slow rotating sequence. And it seems like by a few 100 million years, they've all gotten to that. And then what you would expect naively is for that sequence to just move up in time. Now it's more complicated out in the M dwarfs, partially because the dynamos here are different, right? These are fully convective stars. They're not generating their winds in the same way. So this picture is more complicated. It's also more complicated because these are just harder to observe. And so we don't have as much information out here, right? As soon as the cluster gets a little too far away, it becomes impossible to measure the rotation periods for these things. But the bottom line is that for the G stars, the picture I just described to you looks like it works. Right? Like they converge onto a slow rotating sequence, and then you take that sequence and you play it forward in time, and it does basically what you think it should with a very kind of standard assumption for energy, angular momentum lost over time, as soon as you move into the K stars, it gets messier. Now it's possible that the G stars do this as well, but they just do it much earlier in their evolution, and we essentially aren't sensitive to it, right? Because the window is much shorter, right? Everything takes longer as you go out to the right here.
With regard to the M3 and later stars,
Yeah.
what's the sort of the thinking right now about whether or not some of these stars are sort of on their way to slowing down and they've gone and kind of reached that sort of upper limit in the rotation period? Or are they all sort of getting born with this huge range of rotation periods, and how could that work?
Yeah.
Thinking about
Yeah, that's a really good question. So it's hard to know. I mean, you don't see quite that range of rotation periods. So I don't think they're born with 25 or 30-day rotation periods. I mean, I couldn't be definitive, but I would be surprised if that were the case. It's a little hard to know because these stars here at Pleiades age, they're actually still contracting onto the main sequence. So it gets a little confusing there because you're combining stars that are slowing down because they're losing angular momentum with stars that are actually spinning up because they're still contracting. So I think what you can probably say is that by Perseppe's age, yes, some of the earlier ones have actually joined this solar rotating sequence, but you still get a wide spread, and that presumably reflects some combination of the angular momentum at birth and then the efficiency of the winds in ways that, I mean, the modelers I know don't even try to model this part. They focus really on getting the sun in particular right, and then, maybe getting out into the Ks, but. And I mean, I don't want to sound like I'm being dismissive. Some of these people are good friends of mine. They just don't, that's just it's a different problem in a sense, trying to understand what's happening there.
It seems to me there's like two groups for the,
Yeah.
like I model this,
Yeah.
the eyes.
Yeah. So, what you're pointing out to is a really hilarious cultural question. So you'll notice on this, the periods are plotted linearly, whereas here they're plotted in log space. And part of that comes down to like these debates about whether there are actually gaps. And people will get into these intense arguments, and as far as I can tell, that comes down often to like how you plot things. It's not it's not really. But yes, I agree. It does look, and it would be interesting to know. I mean, that could reflect the fact that the transition from being very rapidly rotating to being on the slow sequence is rapid, right? And so you just don't see many stars in that. But I hesitate to make too much of those kinds of things because I think it's easy to get fooled by your eyes. Yeah.
Any questions? Yes, please.
The end of star is born extremely fast rotate than the stars. It's like 15% star composition the end of star, some of the end of star is way below this plot, which means the very fast rotate. This means that they are initially fast rotate.
Yeah, so I think the assumption would be that they probably also at birth. So it's complicated here because again you have to keep in mind that there's a delay in when these stars actually join the main sequence relative to the other ones, right? So we consider Pleiades to be our sort of zero-age main sequence cluster, but it's 120 million years old, right? It's not zero. And it's 120 million years old because that's how long it takes for, let's say, the G and early K stars to get to the main sequence, but the M dwarfs are clearly not there yet. Okay, so there's a sort of masked delay here that by the age of something like Coma-Burr or Perseppe, you think has been erased. Like you've kind of lost the difference in terms of joining the main sequence. Anyway, my point here is I think you would still say, oh, these are likely born between 0 and 10 days, give or take. I mean, I'm not a star formation expert. I know there are lots of people here who are, so I don't want to get too carried away here. But my sense is that that's a reasonable range for them to be born with. And then anything that you see that's rotating more slowly, and we don't have, and I should say, there's a bias against finding those stars, right? Like a low mass M dwarf that is rotating really slowly is a very hard thing to measure, right? These are 20 or 30 day rotation periods on really faint stars where you're not getting a lot of contrast, because these are spots on the star that you're seeing rotate in and out of your line of sight. And so you expect to be pretty incomplete in here, right? I don't know if I'm quite answering your question, but I guess I would say two things. One is that I still think that this kind of reflects what you expect in terms of the birth distribution. And the second is that we're not super sensitive to actually what's happening in here, just because those are harder to measure.
Yes, I was just wondering, on that point, is there any worry about an observational bias between, I've always worried that we treat stars as very sort of homogeneous when there might be quite a bit of difference between them. Could there be an observational bias? They're all at the same distance, for example. So these stars, we're measuring rotation periods from some of them because the stellar activity is rising above the noise, whereas there's some of them that we have to throw out because we can't measure our rotation period. Any chance that there's some physical differences between those stars that are getting sort of lost in terms of
Yeah.
ones that show a lot of activity?
So I think what I would say is, to first order, no, I'm not worried about that. And then to second order, sure, but, okay? So the reason I'm not super worried about that is that I just think we're in a completely different regime now. You know, when we had like 15 measurements in a cluster, then you start to really worry about like how representative is that of that cluster, okay? That's not the case anymore. We have light curves for essentially all the stars, and you can pretty much convince yourself that you're measuring, you are measuring a representative set of rotation periods. Like, I won't try to convince you if you don't want to be convinced, but I would say I'm not super worried about that. You expect that some of the stars will be pole on and you won't see, right? So there's some fraction for which you expect that you're not going to measure rotation periods. But unlike V sin I, for example, you're not actually sensitive to inclination effects in the same way. So I would say that it gives you a pretty unbiased sense of what the rotation period distribution is. Now, the one thing that ignores completely is cycles. So as I mentioned, we know the sun goes through a magnetic cycle, and that impacts its magnetic activity, and that would presumably impact how well you can measure its rotation period. And so if any of these stars are subject to those same kind of cycles, then again, you would worry that you're not going to necessarily detect the entire population. What I will say is that we looked at this with Persepi, where we had multiple years of K2 observations of the same stars, and we essentially saw no evidence for cycles. We actually saw that rotation periods were fairly robust over 3-5 year baselines. So my guess is that there is some cyclical stuff, and that might explain why you don't get measurements for every star you have a light curve for, but I'll go back to my first point. No, I'm not. Yeah, I'm not super worried about that. Yeah. I guess I will worry more about that when I have like tons of M dwarf measurements. Yeah.
Any more questions? If no, let's thank Marcel. Okay.
Thank you.